For this hour, we're going to talk about verifying code using automated reasoning. My name is Remy Delmas. I've been with Amazon for 3 years. I'm in a team that develops automated reasoning tools for the Rust language, which is what we're going to talk about today. And prior to that, I worked for 15 years in the transport industry. I was developing and using automated reasoning tools to verify railway control systems and flight control systems. So let's dive in. So this session is level 400, so we're going to dive deep into how the technology works and how you can use it. So if you're a Rust developer, you want to know more about this technology, you're in the right place. If you're a manager who wants to know more about how you can improve the quality of your software you're developing, this is also the right place to be at this time. So we're going to go over what is automated reasoning, why do we want it, what does it do for you when you use it. Then we're going to deep dive into the Kani verification tool, and then we're going to wrap up. So I'm going to cite our VP. I'm part of the automated reasoning group at Amazon. And Byron Cook says, automated reasoning focuses on the automation of formal logical reasoning to raise the bar on the security, the durability, availability, and overall quality and correctness of systems, software systems. And it uses mathematical foundations in order to model and analyze the behavior of systems. So what is not automated reasoning? So automated reasoning doesn't look at historical data of a system to predict future behavior. We're really using formal models of the system, and we're analyzing the models to prove the correctness of the model and hence of the software that's modeled. And I was quoting Neha Rungta, which is the director of applied science for Amazon. So there's two key parts. First, you have to model the system you want to analyze, and then once you have a formal model of the system, you can ask questions. And automated reasoning brings you yes or no questions, and these questions are mathematically rigorous, and you can trust the answer of the tools because it's built on a theory that ensures correctness. So I'm going to go briefly over the timeline of automated reasoning. So automated reasoning as we know it today is actually rooted in a century-old discipline and branch of mathematics that was aiming at formalizing rigorously the foundations of mathematics using mathematical logic. So at the early 1900s to 1930s, Boolean algebra was discovered, so how do you reason on propositions that can be true or false. And then this gave hope for all the people in the mathematics community back then that we could rigorously formalize the core of the mathematics and then automate all reasoning we could do in mathematics. Unfortunately, by the 30s, some people had dived into his questions, and Gödel's theorems, incompleteness theorems, basically told us that not all truth could be proved. And back then, that was a time of mechanical computers, so this branch of mathematics was not really related to computers at all, it was just mathematics. So skipping over to the 40s, 50s, we started seeing some abstract models of computation being proposed by Turing with the Turing machine, or by Alonzo Church with the lambda calculus. Two abstract models of what could be a computer theoretically, but that's what before computer existed. And then over the Second World War, digital computers started appearing. And then fast forward to the 50s, 60s, people started looking into how can we automate reasoning on Boolean formulas. And that was the SAT problem and the first algorithms to solve it. And then back then, compilers were starting to appear too for digital computers. And Hoare logic was a proposal by someone for Tony Hoare, to how can we reason about programs. But back then it was just pen and paper proofs you would do on the side, and then you would just run the program and make sure it's working as intended. Then we had the weakest precondition calculus, and then came the idea of what if the compiler could actually use these mathematical reasoning principles to actually prove the correctness of your code. And the very first people to industrialize that kind of approach were the hardware people who were building processors that were getting more and more complex. And they started using binary decision diagrams to exhaustively check the behavior of CPU designs before building them, and then SAT solvers, which solve the Boolean formula that describe the behavior of programs, became so powerful that we could start using them on bigger and bigger problems. And then by the 2000s, all these things became fast and powerful enough that we could start using them for software. And separation logic was invented, which lets you reason about how programs handle memory. And then symbolic execution came to be, which is the technique we use today to translate code into a logical model that we can analyze. And today, like Amazon has tools like Daphne, CBMC, Kani, which are used to develop industrial applications that are fully verified. So key to all of this and enabling this today is like long century of work on building formal models of computation and also building algorithms that can actually reason on the model automatically for you and let you answer questions about the behavior of your systems. So now we're going to go into how does automated reasoning differ from testing? Because that's an important notion. So I'm going to start with a very simple example. This is a Rust function, has 4 inputs ranging over the integer 64 bits, returns a single integer, and I modeled if then else if condition that guards a portion of the code that can panic. And so now I'm asking you the following question: can this function panic? Which means, is there any way to find a value for A, B, C, and D that lets you enter that branch and trigger the panic in the code? So how would you do to answer this question rigorously and give me strong assurance that the code can panic or cannot panic? So if I want to prove the code cannot panic, I can try to do fuzz testing. I'm going to sample a number of inputs randomly, input values. I'm just going to execute the code. This is only going to give me a very partial, confidence in the behavior of the function. If I really want to establish a strong guarantees that holds for any possible input, and I was using testing, I would have to do something like this. I would have to basically loop over the whole input domain of the function, invoke the function, and see what it does. Let's say I want to do this exhaustive testing. This would take me 2 to the 256 iteration of that inner loop. And even assuming I have a very powerful computer that does 1 iteration every nanosecond, it would take me 10 to the 60 years, which is much more than the lifetime of the universe, to actually exhaust that input range. So this is clearly not feasible. So that's the problem we're faced with software, is that most software is too complex to be exhaustively tested. And that's what automated reasoning provides an answer for. So I want to step back a little bit, and I'm going to talk about automated reasoning at Amazon. So why do we do it? How do we do it? So we're trying through automated reasoning to establish this virtuous cycle, which is we invest in developing automated reasoning tools, and then we use these tools to develop products that are customer-facing. And then we get the feedback from applying the tool, we improve the tools, and we improve the products that use the tools. And so overall, what we see happening is that automated reasoning, you have an initial cost in getting to use it, but then ultimately it lowers the cost of your development. It helps you build better products. And once you get good at it, it also helps you develop faster. Because you spend less time testing, you can find all the errors ahead of time, and you never basically have to backtrack on your design and development. So here's an example of the more well-known products that Amazon has that use or were developed by using automated reasoning. So Code Guru Reviewer has some of that inside. Amazon Inspector uses SAT solvers to perform network reachability. IAM Access Analyzer that was discussed at Inforce this year too. The Amazon VPC Reachability Analyzer. These are all tools that analyze the soundness and correctness of the policies you use to configure your VPCs. But today, we're going to go one level down, and we're going to look at code verification. So the tool I'm about to talk about is targeted at Rust code verification. But so first I want to talk about Rust itself. So for the 8th year in a row, Rust is the most desired programming language according to the Stack Overflow study. And 80% of people who use it want to use it again. So it's a very good tool. I like it too. And safe Rust is a big deal. It brings you a lot of guarantees. So it does type safety, initialization checking, so you never handle undefined values. The borrow checking that the type checker does ensures that you cannot have race conditions on memory locations. You can not have concurrent updates. You can do safe concurrency because the type system tracks and distinguishes types that can be safely shared between threads or safely moved across threads. The language itself is super high level. It has zero-cost abstractions that let you structure your code at a very high level using trace modules and everything else. But these abstractions don't have any runtime cost or very little cost. And thanks to borrow checking and lifetime inference, you also get rid of garbage collection because the compiler knows when your program stops to use certain memory and can free it for you automatically, and you get super good runtime performance. But I think something that's also worth mentioning is the package management system. Cargo is really sleek. The documentation is really good with Rust, so everyone loves that part of Rust. So opt into Rust and you're going to get all these nice guarantees if you stick with safe Rust. However, there is another side to Rust. It's unsafe Rust. And that's for developers who want to basically bypass some of the safety provided by the type checker of Rust and let you do things that are not as safe. And so basically when you step into unsafe Rust, all the correctness guarantees are on your on your end. You have to enforce security yourself, safety and security yourself. So unsafe Rust lets you disable the borrow checker. It lets you do delayed initialization of memory. It lets you cast values in place. It lets you do unchecked arithmetic operations that can potentially overflow. So you have to ensure that there's no overflow when you do such operations. And it also lets you access memory directly through raw pointers. And so when you use these pointers, you have to make sure that all pointers are going to be in bounds of the allocated memory. And when you do arithmetic on these raw pointers, you have to ensure that there's no overflow and that you're not going to create dangling pointers. And it also lets you call into external code that could be through the foreign function interface, and that could be C code. And then you basically are on your own and you need to ensure correctness yourself. So if you're asking yourself, yeah, that doesn't seem really used a lot. Like, I've been doing Rust for a while. I've only used safe Rust. I've never had any problems. I never had to escape the type checker to do some more like tricky things. Actually, the Rust standard library is really a highly leveraged and critical component of Rust, of the Rust ecosystem. And if you look at the code of the standard library, it uses thousands of unsafe blocks. So all these unsafe blocks are here to allow more performant implementation of the primitives, and they're wrapped into safe interfaces. But still, unsafe Rust is a reality, and automated reasoning for us is the proper way to ensure that your use of unsafe Rust is actually correct. So Rust at Amazon. So adoption is growing every year. So Rust is one of the, or if not the fastest growing language inside of Amazon. We have multiple services and applications adopting Rust or being ported to Rust. And Amazon as a company is invested in Rust heavily. So for instance, in 2019, Amazon announced the sponsorship of the Rust Foundation. We've been hiring key technical leaders of the Rust community, like Rusty compiler developers and design lead and everything. And we also have for plans for ourselves to start verifying parts of the standard library. So below here, Firecracker, S2N, Tokyo, Bottle Rocket are all examples of products, internal, projects at Amazon that use Rust. So this leads us to how does automated reasoning come in the picture. So I'm part of the team that develops a tool named Kani. And this is an open source tool that does automated reasoning on Rust code. And it was created at Amazon and released free of charge for everyone to use. So the foundations of Kani are mathematics and mathematic proofs of Rust code. And it allows you to check for properties like absence of overflow or underflow with integers, memory safety if you use raw pointers, custom properties if you have custom assertions. And so the key distinguishing feature of Kani with respect to other tools for Rust is that Kani lets you verify unsafe code blocks in Rust. So all these raw pointer manipulations, unchecked arithmetic operations, Kani has your back if you use the tool for that kind of software. And so below is a list of projects that use Kani and have proofs deployed in production. So Firecracker, S2N, Hi-Fi Time is an external project that does time conversion, and Rust Bitcoin is also using Kani to verify the correctness of their code. So I'm going to zoom into one of our users' stories. So this is about S2N Quick. So it's a library by Amazon that implements the Quick protocol. And they've been using Kani heavily to verify the correctness of their optimizations, performance optimizations that use unsafe Rust. And they have a blog post about how they use Kani to discover errors in their handling of the integer, like the variable length encoding of integers in the S2N Quick protocol, and also how they use Kani to check that the optimized version of a Rust method performs exactly the same function as the reference method. So please consult the blog post for details. Firecracker, so it's a virtual machine monitor written in Rust. And they've been using Kani to verify key properties that ensure separation of VMs and separation of the traffic. So Firecracker tries to enforce rate limiting on network communications for a VM. And thanks to Kani, they were able to discover a bug in their implementation that would have resulted in allowing more bandwidth than specified for a particular VM. So I refer you to the blog post as well for more details about that. It's a really cool blog post. So now we're going to go into a deep dive. And this is going to be going into the inner workings of automated reasoning. So coming back to our initial example, exhaustive testing doesn't work, so what do we do? So so first of all, I'm going to show you what's the experience like when you're using a tool like Kani. So we take the same function, and we're trying to determine if the function can panic or not, and if it actually returns 0 all the time or not. So with a tool like Kani, you would just start by writing a simple, what we call a proof harness, which looks very much like a test harness. So it's a Rust function that's tagged with the Kani proof attribute. And the preamble of this function allocates inputs for the function under test, under verification, and then just invokes the function, gets the result, and asserts that the result is always equal to 0. So the main difference here is that the Kani : any is what we call a symbolic input, and it's a non-deterministic input that can cover the whole range of the type. And it also tells the proof engine that, you have to consider all possible values for this input. But there's no looping here. We're declaring symbolic inputs to be able to reason about them, but we're not going to systematically exhaust the range of the type. And then you invoke the tool, and the tool comes back to you with a result in less than a second. And the answer is the assertion can never fail, and the code can never panic in less than half a second. So what does Kani do that testing doesn't do to be able to give you that answer in such a short amount of time, and how can you trust that this answer is actually correct? We're going to look into this. So now I'm going to ask for you to focus for 3 minutes and stay with me. This is going to be one of the lengthy parts of the talk, but it's really about explaining what reasoning on code actually means. So our goal is to prove that there's no valuation of A, B, C, and D that can satisfy the branch condition that guards the panic. So I'm starting with this formula, A less than B, and B less than C, and D greater than 100, and A greater than C, or D less than 28. So I'm going to use a number of proof rules that I'm going to apply to this formula. And my goal is to build an actual proof. And by building a proof, my goal is to convince you that the conclusion is actually the right one, the conclusion I'm going to reach. So let's start looking at the formula. What can we do? So first, I see that this conjunction here, this and sign, is guarded over the disjunction that's inside the parenthesis. But I can go to the basic rules of Boolean reasoning, and I know that I can distribute and over or. So I can rewrite P and Q are R to P and Q are P and R. So let me apply that rule R1 to the current formula that represents the guard of the if, and I get this new formula. So what can I do? Now I'm going to focus on a different part of the formula, this one here. Two propositions, D superior than greater than 100, or A superior, greater than C, or equal to C. I have another rule in formal Boolean logic that I can use here to just swap the left and the right. Because I know for any propositions, P and Q is equivalent to Q and P. So let's apply R2 and do that. I get this new formula. What can I do now? So now I'm going to look into the arithmetic part of the formula. So I have here A less than B, and B less than C, and A greater or equal to C. Greater than or equal to C. So I know just from basic integer reasoning that whenever I have x less than y and y less than z, then x is necessarily less than z. So that's the situation here, the green arcs. But what this formula in the code here is asking is for A to be greater than or equal to C. And based on this R3 rule, I know it's not possible. So what I can conclude from that by applying R3, that this whole part of the formula reduces to false. I'm never going to be able to find anything by virtue of R3. So I can simplify the formula further. And now I can use another rule from Boolean logic, which is false and anything else is equal to false. False basically absorbs everything else with conjunction. So I can further reduce the formula and get to false. Now I'm going to focus on false or something else. So false or something else is equal to something else, which is why I can simplify false away. And I can continue like that applying rules until I reduce the formula enough. So this one is going to reduce to false again by virtue of R3. Then I can swap rear to the terms another time, apply absorption, and I can conclude in the end that this big formula we had to start with, it actually reduces to false. And the evidence I give you, the proof of that, is just I give you the sequence of rules that I use to get there. And I give you the rules. And if you trust that these rules are correct to begin with, and you can just replay the proof steps, then you can convince yourself that what I'm telling is actually, like what I'm telling you is actually true. So, and I can conclude that panic is unreachable. So I want you to understand two things. Once I give you a proof, you can check it, and that's fairly easy. The hard part of this is finding the proof in the first place, finding which formulas to apply the reasoning steps to, and finding which proof rules from mathematical logic I can apply to simplify my formula. And that's the hard part. And thankfully, thanks to all the research work that's been done over the past century, these proof search techniques have become so efficient that we can apply this type of reasoning on code at very large scale. And that's basically automated reasoning 101 for you. So now I'm going to look at the practice of using an automated reasoning tool. So Kani is symbolic model checking for Rust. So symbolic because we manipulate formula, and model checking is because we reason and basically reason over the whole model of the code, and we were able to get conclusions about its behavior. So Kani as a tool takes your Rust crates that you wrote yourself, can load them into the tool, also loads the Kani crates that ship with the Kani tool itself and lets you use the symbolic inputs to specify your test cases and your symbolic test cases. The role of Kani is basically to translate your Rust code into this automated reasoning engine that performs the style of reasoning I just showed you. So while doing that, Kani also injects a number of extra assertions in your code or translated code in the model of the code. And it lets you check for built-in properties. So the tool is going to check for you the absence of panic, the absence of pointer overflows, the absence of dereference of pointers that are out of bounds, the absence of arithmetic overflow or underflow, the absence of division by zero, and the absence of overflows when converting from signed integers to unsigned integers. And it can also answer basic questions about, is this location in my program, is this line or branch reachable? What are the inputs that let me get there? It can also analyze user-defined properties that you add yourself to your code using either inline assertions in your code or function contracts. So you can say, this function here requires that the inputs satisfy some condition, and in return, I guarantee that the output is going to satisfy some condition. And since we're based on sound mathematical reasoning, the tool can give you two answers. Either your property holds for any possible input to the function under test, as specified by the symbolic inputs that you declared in the test, or it gives you the answer, the property doesn't hold. I found a case where the assertion fails. And in that case, the tool is able to provide you with a test case with concrete values for the function inputs that are going to trigger the actual bug. And you can close the loop by launching your debugger and actually inspect the counterexample. So sometimes the tool runs out of memory, or you don't have enough patience to wait for the results and you're going to Control-C it. But the tool is never going to give you a wrong answer. So if you want to use Kani today, all you have to do is to install the latest version using cargo. So cargo install Kani verifier, and when you invoke cargo Kani setup, it's going to download all the dependency in the reasoning engine it uses to analyze the code. If you're on GitHub, you can also use the GitHub action, which lets you trigger a run of Kani analysis at every PR. You can also configure it to block your release pipelines. And if you're actually developing a REST and want to use the tool in an interactive way, you can use the cargo, the Kani VS Code extension too. All right, so taking a step, now I want to show you how it is to use the tool in practice and the shift in mindset that it requires as a developer. So once the verification tool is in your development loop, we shift into a mindset of proof-guided development. So test-driven development, you start by writing the tests before even writing the software. It's kind of the same idea. You start by writing the proof harness and the properties you want to check before even starting to implement the function. So let's say I'm going to use an example to guide this part of the talk. So let's say you've been tasked with implementing a basic container for a vector of bytes, and you want this array to be this byte array to be resizable, this byte buffer, and you're going to track the total capacity that's allocated, the capacity that's used, and you're going to start with an inline byte buffer of some small capacity, so that you can do stack allocation if you want. And when this capacity is exhausted, you're going to transition and allocate dynamically on the heap. And once you're there, you can resize. So initially you start with a default capacity. Once it's filled up, you start using the heap storage. And if you exhaust the heap storage, you just resize it. So that's very basic. That's what vectors are in the Rust Standard library, for instance. And let's say you want to make this super performant, so you're going to use unsafe Rust to handle all the heap allocation and heap access. So you're going to start by writing the interface of the byte buffer like that. And a key notion here is the invariant. So for your type to be well behaved, you want some properties to hold all the time, like the use capacity should be always less than the actual allocated capacity or equal. And you're only going to transition to the heap when you're actually run out of space, which means as long as the use capacity is less than the mean capacity, you don't want a heap pointer, but then you want to allocate on the heap. So that would be the invariant you're trying to maintain on the data structure. And then what you want is to establish the invariant when you create the object, and then you want to maintain it as you push and pop from the buffer. So proof-guided development, you're going to start by writing a few proof harnesses. Let's say the following. So for the new harness, you allocate a byte buffer using the new method, and you just assert that the buffer invariant holds. For the resize function, it's the same. Allocate any buffer non-deterministically, allocate any number of extra bytes you want to store in there, and invoke the resize method, and check that after any resize, the invariant is still maintained. Same for push and pop methods. So you start by writing these very simple proof harnesses, and then you invoke the tool, and what you hope for is that the tool tells you, oh, success, you implement the methods in the meantime, and then you run the tool, and you're hoping that everything's going to be proved in a matter of seconds. What it actually looks like in practice is more like that. You start, and then the tool tells you, oh, you have a multiplication overflow possibility in your resize logic. Oh, your unsafe code is trying to unwrap a non-option. Or, oh, you have an out-of-bounds pointer dereference that's possible under certain conditions. Or your inline assertion that you added yourself is actually failing for some inputs. So the tool is going to find any needle in the haystack, and it's going to report to you all possible failures for any generic property or your own assertions. So how do we go about debugging fail proofs? So I'm going to look at the logic we use to resize the buffer as an example. And the shift in mindset is even before starting to implement the resize method, you have to ask yourself, what do I want this function to do? And the answer in that case would be, I want my resize function, given a current capacity and a requested capacity, I want the new resized function to return the smallest power of 2 possible to hold that capacity. And so you're going to write this function that gives you the initial capacity and the requested size and the resize capacity, and you're going to check that it actually satisfies the property you want for any possible values. So the capacity should be a power of 2, it should be greater than the requested capacity, and it should be, if you divide it by 2 or if it's 1, then it should be smaller than the requested capacity, which shows that it's the smallest power of 2 you could have used. And that's the correctness criteria for your resize function. And then you can start with an initial implementation attempt. So give me an existing requested capacity. I'm going to give you the smallest power of 2 that I can find. I start from 2, and I just multiply by 2 the current value until I find something that's greater than the requested capacity, and I return that. That seems correct to me. So I'm going to write a proof harness that just takes any requested capacity, computes the smallest power of 2, and just asserts that it is actually the smallest power of 2. And the tool tells me no, that's 2 things happen. First of all, you have an overflow in the multiplication in your code, and second of all, due to the overflow, the function returns something that's actually too small to hold the requested capacity. So what you can do from there is click this button here, ask the tool to provide you with inputs, concrete inputs that reveal the problem. So you start by looking at the counterexample. So this is how a counterexample looks in Kani. And it basically has this vector of values that specify concrete values for the non-deterministic inputs, the symbolic inputs, that actually reveal the bug. And from there, you can start the debugger and execute the program on that. And once you're in the debugger, you can see how the bug happens. So in that case, if the requested capacity is too high, After a number of iterations of that loop, you're actually going to overshoot the range of I64 and trigger a panic and return a bad result. So after using the tool, you converge to this solution. You have this extra assertion that basically is here to tell the user, oh, don't invoke that function with the requested size that's too large. Otherwise, we're guarding against overflow here. Ensure that the requested size, return size is going to be 1 if the requested size is 2. And then that loop that computes the power of 2. But this time, the multiplication cannot overflow because we're basically added a precondition that says we don't handle requests that are too big. And now you take the same proof harness, run the tool, and success. So now you know that your function is correct. And what can you do from here? If you want to push it further, you can optimize your code. You can transform that loop into a number of bitwise operations. And you can also check that the property still holds. So what you've done is optimize the code, and you've checked that it satisfies the exact same properties than the code before. So this one is less readable, the one was more readable, but now you're actually sure that they both do the same thing. So now let's look at the resize function. So this was my initial attempt at writing a resize function. Give me the current capacity and some extra bytes I need to accommodate. I invoke the resize function that tells me if I need to increase the capacity or not. Then I have a number of unsafe code constructs here to allocate memory on the heap, or resize the existing heap allocated memory if it was already there. Update the new capacity, and that's it. So this code, by the way, has unsafe code in it. That's really unsafe. It lets you do bad things with the memory. The tool finds all the errors as shown earlier. After using the tool, I converged to this solution. I was basically forced by the tool to handle all edge cases, handling non-values, fail allocations, and everything. And this tool passes verification. And now I know that my usage of unsafe code is actually safe. So now I'm going to dive one step deeper into how does Kani actually do that, and how does it build the model that's used to reason about the code. So I'm going to use the smallest power of 2 function. We look at the code as through the control flow graph of the code, which means we have a bunch of nodes which hold the straight line portions of your code, and then we have edges connecting the flow of control between these straight line portions. So here we have the initialization of n, and then this looping construct in the middle is a while loop. The exit leads you to returning n. And so what symbolic model checking does is build a logical formula from that control flow graph by symbolically stepping through the graph and emitting a little portion of formula every time. So if I step in this first block here, I'm going to emit a small formula that says initially the value of n is equal to 2. When I step into this conditional, I'm going to emit a little bit of a formula that says, oh, the control flow condition here is n0 less than the requested size. And I add a negation detail. So this condition can be either true or false. I don't know because I don't have this. The rec is a symbolic value, so I don't know what it's going to be. So I have to consider both cases. One case is I'm going to exit the loop right there and return the value n0, or I'm going to step into the loop and actually multiply n by 2. But in that case, since this operation can overflow, in my logical model, I'm going to instantiate p0, which is the condition under which the multiplication would overflow. And I'm going to keep, and then I'm going to update. I'm going to say the n is going to be updated as 2 times n0, n1. And then I can step through the loop a number of times symbolically like that and generate this formula. And after a number of iterations, I'm going to stop. And this is what is called bounded model checking, because we only explore the code up to some depth. But we can check that we've explored it deep enough inside the loops as well. And once I have this logical formula, I can use the reasoning engine and ask a bunch of questions about my model. So is it possible to satisfy C0, which means exiting the loop at this first iteration? Question is yes, it's satisfiable, so I can exit the loop. Second question is, can I step into the loop? If I step into the loop, can I satisfy the overflow condition or not? The answer is yes, every time. I can step, and I end up at the 62, iteration number 62. The solver, the logic solver, finds values for the input that let you trigger the overflow conditions. And that's what eventually is reported to you as a counterexample. So the message here is that you write your code, and the translation into a logical model and the analysis of all these basic properties of your code is completely automated. Okay, so now I hope that I convinced you that it's really different from testing, this approach, but it's also highly automated, and using it feels like basically writing tests. So the takeaways, benefits of using a tool like Kani. So proof harnesses are very similar to traditional test harnesses. They look the same, and they're very simple to write. But when you start using this, you have a very higher return on investment for your time. And so if you're doing safe Rust, you already have all these nice memory safety properties. And if you're going to have to write tests, you better do symbolic tests and use Kani. You have no excuse for not trying it. And when you do that, you can go into functional correctness for your code. Like we saw for the resize function, I can tell you exactly what I want my code to do and make sure it does what I want. If you're using unsafe Rust and you're not using Kani, you have no excuse either, because unsafe Rust, everything rests on you as a developer to enforce correctness and make sure you don't break all the guarantees that safe Rust provides. So you really have to use Kani because it gives you better results than just testing alone. And the takeaways also is that there's no real barrier. It's available in Cargo, GitHub Action, VS Code extension. You also have an integration with a fuzz testing framework, Bolero. So this is interesting. So if you're used to using fuzz testing, use the Bolero framework. Start by fuzzing your code like you would do normally. Then in Bolero, you can flip this option that tells you that tells the tool to use Kani as a backend to run the tests, the fuzz tests, and it replaces the fuzz testing by this symbolic exploration of the model of the code. So you should definitely try Kani at least once, but not as so easy and nice. Kani has limitations. So what you'll find when you start using automated reasoning is that you have to decompose your code, and you have to identify the functional properties and the safety properties you want to ensure, and you have maybe sometimes to be much finer grained than you would be usually. So it forces you to reason and to structure your code differently and to reason about what the properties should be for your code. And Kani has scaling limitations too. Not all Rust programs can be analyzed today, far from it. Anything that has floating point is going to be hard. If you have long-running loops that need to be unwound hundreds of thousands of times, it may not work that good. Or if you have concurrent or asynchronous code, we don't handle that at the moment. And we also don't detect all possible undefined behaviors that Rust has and unsafe Rust has. So if you're familiar with the stacked or tree borrows, we don't do that yet, but we're working on it. So the future of Kani. So the message here is that Kani is actively developed and supported. We're working on adding new features that enable better scalability, like compositional reasoning, stubbing functions out with abstract models to scale verifications, function contracts, loop contracts to go beyond the unwinding we do and do unbounded reasoning on loops. And Kani is really a long-term commitment for Amazon because we use it internally, and we also have a lot of external users of the tool. So if you start using Kani, you can trust that it's going to be around for a while and the tool is going to be supported. And another thing we want to announce today is that we're going to be using Kani to verify the correctness of critical parts of the run standard library. And this is our way of helping the community make sure that the foundations of Rust are correct by verifying the parts of the standard library that are the most critical and use unsafe code, basically. So if you want to follow our efforts, please check out this URL and flash the QR code. So I want to conclude by just saying, like, please give Kani a try. It's going to take you maybe a day or two to get used to the way of thinking about proofs, but you're really going to get some nice results on your code. And here's a summary of all the resources we used in the talk. And I really want to give a shout out to all the team. I'm just the messenger here, so we have all these people working on the tool. They have been for years, and they work day in, day out, improving the tools and making it better for everyone. So thank you. And please don't forget to complete the session survey in the mobile app and tell us if you enjoyed the show. Thank you.